So how do I translate? So this is how, this is stack pointer and this is x and y. If I get an arithmetic instruction like add, sub and r, first I will do at sp, sp will give me the address of the stack pointer. So let me say sp is say 268, this is RAM location 0 and that is 268. When I say at sp, your A register will get 268. When I say A equal to M, A will be A of M of 268. Sorry, A equal to M. When I say at sp, A will get 0. When I say A equal to M, the A will be M of 0, so A will get 268. Now I say A equal to A minus 1, so this will become 267. Now D equal to M, M of A, which is M of 267. This will be now whatever Y. Now A equal to A minus 1. So A becomes 266 because A has already 267, now 266. Now I now say M of 266 is equal to, what is M of 266? So 268 is SP, so this is 268, 267 is Y, 266. M of 266 is equal to M of 266 plus D, this is X plus Y, right, and this will be stored at 266. So 266 now will get X plus Y. Again I do at SP, A is 0, I do M is equal to M minus 1. So M of 0 is equal to M of 0 minus 1. So your stack pointer now will become 267. So this will now start pointing to this. So what I have done, I have retrieved X, I have retrieved Y. First I retrieved Y, then X. For that I went to the, went to the stack pointer, got the value of the stack pointer into my A register, decremented it, copied the value of D, X, Y onto D, right, that is D equal to M, and then decremented my A register, that will now point to X. Now I added that memory with this X plus Y, I get that. Then again I went back to my stack pointer A0 and decremented it, so to pop it. Suppose instead of doing at, I can say at sp A equal to M, A equal to A minus 1, right. The way to decrement SP can be like, I can say at SP, so your A is becoming 0, D equal to M of 0. So let us say SP now is 267, so D will become, so originally it was 268, right, to start with. So SP will become 268. Now I will say D equal to D minus 1, so D becomes 267. Now I say M is equal to 3, so M of 0 is equal to 267. So this is also another way of decrementing your SP. So let us compare these two now. I prefer to do this one because there are only 2 instructions. If I execute this, then this will be 4 instructions. So by having 4 instructions, I am going to spend 4 cycles to decrement SP, while I can finish this off in 2 cycles. So my program is 50% faster with respect to this code. And the second thing is, when we go in for embedded devices today, one of the important thing is that my memory has to be less in size. the amount of memory taken by my program has to be less in size, right? Why should the memory be less in size? Because these embedded devices, especially in the IoT, Internet of Things, they are going to be small devices running with battery. Memory consumes lot of power, right? If I have a system with large GBs of memory, it consumes more power. So these small systems that we throw, say for at different places, say for temperature sensor or stuff like that, these are going to be very small devices. They are going to consume very less power. So your memory has to be very less, right? And if my program that I am compiling is large, it cannot fit into that memory, then we have a big issue. So always your compiler should generate, especially for embedded systems, should generate small amount of code. Your compiled code should have as less instructions as possible. So in that context also, this makes a lot of sense, right? I would like to have this this way of decrementing pointer rather than this way of doing this rather than doing it this way. So I get 50% reduction in storage and also 50% reduction in execution time by doing. This is what we mean by compiler optimization. This is what we mean by compiler optimization, right? And very importantly, the other part that we need to keep in mind is that, okay, this particular add, this makes sense, this 4 to 2 cycles, suppose this add is executed 1 million times. By using this decrement, I will be spending 4 million instructions. By doing this decrement, 2 million instructions. So the saving is 2 million instructions if this particular add is going to execute million times. Now, how can an add execute million times? Obviously, if it is in a loop, right? We have written loops, right, in the assembly program. If it is in the loop, of course it will now a single add is in a loop of 1 million iterations. It will execute million times, and every time it executes, this increment that you see on the right hand side is 4 and that is 2. So you spend 4 million and versus 2 million. So that is also something that we need to, even though per instruction, if I am just removing one instruction per translation, that essentially can translate to millions of instructions being saved, or millions of execution cycles being saved, right? In this context, I should also talk to you about this, what you call as 90-10 rule. So I have a program, say, which has 100 instructions. There will be a core set of 10 instructions, and suppose this program is taking 1000 units of time. There will be a core set of 10 instructions which will use 900 units of time. The remaining 90 instructions, say 900 milliseconds, and the remaining 90 instructions will take only 100 milliseconds. Why these 10 instructions alone take 900 milliseconds? These 10 instructions are in a loop. So always 90% of your program will take 10% of your time. 10% of your program, 10% of the instructions in a program will execute for 90% of your time. This is an empirical, if you ask me for an analytical proof, I don't have, but this is an empirically validated software engineering theorem, the software engineering rule. It's called a 90-10 rule. So 90% of your program will take only 10% of time, 10% will take 90. If this add is, normally these arithmetic operations will be in that 10% code, and that will take a lot of time. So optimization, I'm just basically giving you a tip of the iceberg of what we mean by compiler optimization, and this is one such at the back end. Now we know how to do for add. Sub, and or, the three other operations are very easy. So instead of this m is equal to m plus d, right, if you write m is equal to m minus d, same code with m equal to m minus d will take care of sub, m equal to m and d will take care of and M equal to M or D will take care of R, right. So, this is how the binary operations get translated. Now, let us go to the next one, unary translation. We have done it for neg. So, again let SB be some 468. So, 468, this is RAM 0. So, this is 467. Very quickly, at SP means A becomes 0. Now, A equal to M of 0, that is the second instruction. A is equal to M of 0, that becomes say 468. A equal to A minus 1, that is 467. M of 467 is not of M of 467. That's done. So, the Y, it will do a bitwise not of this. Now, the stack need not be pointer need not be decremented, just I am taking Y and I am popping Y and I am making negation of Y and I am not of Y and I am writing it back. So, this works. So, the stack pointer remains the same, there is nothing. So, I am pushing, popping and again pushing it back. So, nothing. So, that's just these 4 instructions. But if this will work for not, if it is for neg, just write M is equal to minus M, that is all. This is for the unary translation. Now, for equal to, less than and greater than. Again, like this is RAM, let SP be say 300 for our reason. So, this will be 300, 299 and 298. So, at SP, so A actually, A becomes 0 here, A equal to M of 0, which is 300, A equal to 299, D gets the value of Y, D equal to M of 299, D is M of 299, which is Y. Now, A becomes 298. So, M of 298 is X, right, M of 298 is X. So, what I am doing here is D equal to X minus, original D had Y here. So, D equal to X minus Y, I am subtracting Y from X. Okay. Now, I have an at label underscore num. Now, whatever I put here in red for underscore num, so we will be having several such EQ in, equal to, less than, greater than instruction, and we have to generate unique labels. So, we make something like A label, which nobody else will use, and this num will be a running parameter. So, every time we encounter a EQ, a new num will be generated and it will be incremented by 2, because we will use 2 labels per EQ instruction. Similarly, for less than and greater than. So, num will be a random. So, initially it will be A label 0. For the first time EQ is coming, A label 0, and I will also use A label 1 here. Next time EQ comes, it will become A label 2 and 3, 4 and 5 and so on. And either EQ or less than or greater than, any comparison operation comes, this num will get incremented by 2. So, we will get unique labels, because in the assembly code I cannot have duplicate labels. So, I will just say at label num whatever D j EQ. If D is equal to 0, I jump to at label num, that is here. And if X is actually equal, D equal to 0 means X is equal to Y. If X is equal to Y, then it should be true. So, I put D equal to minus 1. Minus 1 in 2's complement is all ones, which is in our case it is true. And when D equal to, otherwise I make D equal to 0. And at label num plus 1 and I jump 0 colon jump, and this is at label num plus 1. So, 2 labels are there here. So, what will happen is when d is equal to 0, that means x is equal to y, I will jump to this num, make d equal to minus 1 and come out. Otherwise, I will make d equal to 0 and I will jump bypassing this d equal to minus 1 to this at a label num plus 1, right. So, what will happen, this is what happens. So, at the end of these two exercises, my d will have the result of the operation, that is, if x is equal to y, d will have true, which is minus 1, and if it is false, then if x is not equal to y, it will be 0. Now, what I need to do, that value of d I need to push into the stack. So, how I do, again at SP, so a gets 0, m equal to m minus 1, I reduce the stack, right. Now, I have taken 2 operands out and I am pushing, so your stack pointer will now become 299 and a equal to m, right. So, a equal to m of, so a is currently 0, a equal to m of 0. So, a now gets 299, again a equal to a minus 1, that is a becomes 298, right, 298, on 298 m equal to d. So, m of 298 is equal to whatever value of d, true or false, that will go in. Okay, that is all. So, this is how EQ. So, if I want to do LT or greater than, instead of JEQ, I can put JGT, then this will become x greater than y, implementing GT. If I put JLT, then this will be j less than y, sorry. This will be j less than y. So, this is how I implemented these 3 operations. The important thing is that I am assigning labels, and a care has to be taken that whenever you assign labels, it has to be unique, and this is how you do EQ, LT and GT. Now, the last 2 instruction this is the, so now we go on to the memory access instructions. So, let us look at so push segment index. So, what are the segments? We have argument, local, this, that, first these 4. This 4 is the case. First and foremost, I need to get a segment code, because push segment index means take the base address of the segment, add the index to it, and to that whatever is there in that location, take it and push it into the stack, that is what, right. So, this particular first part of the code will generate the, will get the whatever I need to push, that will be available in the D register. What I just say, suppose I say push argument index, I have to say at arg. At arg will give me the base address of the argument segment. Now, the D, so A will be, so at arg, so the A will now become, arg is stored somewhere, right, 0, 1 or 2, whatever. So, A will get that 2 here, right. A will get argument is 2, right, argument is 2. So, A will get that 2 here, D equal to m of 2. So, D will get the base address of the segment. D has base address of the segment, whatever segment you are asking for. Now, this code is valid for ARG, the argument, local, this, that. These are the 4 segments that we can give first. Then at index. So, this is, just take this index. So, we should say if it is 5 or something, so that, so A will have that index value. Now, I am adding A equal to A plus D. So, this will give me the exact address from which I need to take the variable, because base plus that index. So, D equal to m of A. So, D will, at this end of this, D will has the value that needs to be pushed. Okay. Then now, this is very simple, at SP. So, this is a stack pointer. So, this will say let the stack pointer be pointing to 270. So A will get 270, A will get 0, so A equal to M. This will make, at this point A gets 0, so A equal to M of 0. Now this will get 270. M of 270 is equal to D. D has the value that needs to be pushed, that will go here. Again I will do at SP, so A gets 0, I do M equal to M plus 1, so this will become 271. So this value gets here and your SP now becomes 271. So this is how I increment the SP, push and increment. So this is true for argument local this and that. For temp, we know that the base address is 5. So the difference between other segments and temp is already explained. When you want to have the base address, I have to go to some memory location and get the base address. In the case of argument local this and that, I have to go to location 0, 1, 1, 2, 3, 4 and get that. But in the case of temp, we know that the base address is always starts at 5. So I'll just say at segment code, so when we say temp, the segment code will be 5. This is the code. If I say pointer, always your pointer, right? Pointer actually points to the base address of this, which is 3. So always pointer will start with 3, right? Because the address of the base of this is stored at 3. We have already seen in the emulation at segment. So if we are saying so it will come at 5 or at 3. So your D will be 5 or 3 depending on this. Now I have an index. So this is 2 or something. In the case of pointer, it can be 0 or 1, right? So that index. So A will have the index. Now A equal to A plus D will give me the address where I need to address from which I need to take the value. So now D equal to M of A. So at the end of this story, D basically has the value that needs to be pushed, and this is exactly, I push it into the stack. The same code, the same thing, I push the value into the stack and I increment the stack pointer. If it is a constant, right, just I say at index D equal to A, because D now has the value that I need to push this. If I say constant 2, I need to push 2 into the stack. So I will put at 2, so basically A will get the value 2 and D equal to A, so D gets the value 2. And so D has the value that needs to be pushed. Again I push and increment the stack pointer. So this is how push will work for the different segments. So we have covered all the segments here, argument local this that 4 of them, and then temp pointer and that, right. Now the last one that is pending now is we have still to talk about static. Okay, we will talk about static a little later. Okay, now let us now talk about pop segment index. So again, what we get here is so this is whatever, the segment cannot be a constant here, right. I can't pop into a constant, right. I can only push a constant, pop into a constant. So I need to generate an error for that. Okay, I need to generate an error for that. So this is at segment code. So for the remaining things, right, the argument, local, etc. This that. This is a code. So we will say at arg or at LCL or at this and at that. So we will get that 1, 2, 3, 4 and D equal to M. So D basically has the base address of the segment. Now at index, so A has the index, so D actually has the address to which we need to pop. The popped value has to go to the address. So D has that address. This address, now I say at R13. As I told you, R13, R14, R15 are temporary storages which we can use, right? They are temporary storages. So I just use at R13 here. So this will give me 13, RAM 13, in which I am basically storing. So M of 13 is equal to D. M of 13 is equal to D. So the value of this address to which we need to pop, that address to which I need to pop is stored in M of 13. So at this, so R13 has the address to which the popped value need to be stored, that is there. Now what we do? Now we pop the value at SP A equal to M. So this will give you, so let the stack pointer be at 298. So this is A will get 0 and A equal to M of A. So A will get now, say let us say 278, A is 278. Now I need to pop, right? I become A is 277 and D is equal to M of 277. So whatever I need to pop, this is, let us say I am popping that, this is the value to be popped is now at D, right? Now at R13, so this will be 13, A equal to M of A. Now A will get, because R13 has the address to which we need to pop, now A will now have the address to which we need to pop. So M of A and D has the value that is already popped out. So M is equal to M of that address is equal to D, right? So the popped value goes to that particular location, right? Now again at SP, again A becomes 0, I decrement the stack pointer using this, right? So what I am doing here, I am getting the value of the stack pointer, I am decrementing it by 1 to get the value that needs to be popped. That value I am storing it in D. I go back to R13 at R13 and I retrieve the address into my A register again to which I need to store this popped value that is currently in D, and I store that value into that particular memory location and I decrement pointer. So this is what we do for pop segment in the case of the segment being argument local this and that. If the this is temp and pointer, then instead of doing D equal to M, I need to do D equal to A, right? Because in the case of temp and pointer, you will get temp, the segment code will be 5 and the pointer code will be 3. So D will now get the, D needs the base address, it will be 5 or 3 depending upon that base. So if this segment, pop segment is going to be temp or pointer, then instead of D equal to M, I will have D equal to A. Ultimately at this end of this particular 2 instructions, D should have the base address, and that is basically 5 or 3 in the case of temp and pointer respectively. So this is how we work with pop. So one of the things that we need to basically look at is what will happen if I say push static some 0 or whatever index. All the static variables will be assigned automatically memory by the assembler. So let your program be xxx.vm. We will just say at, we will define the static variable as xxx dot say index, right? This is the variable, and now your D will become yeah. Right, D equal to M. So at xxx dot index will be the address of that variable, because this will automatically D equal to M. So D will have the value that needs to be pushed. So once D has the value that needs to be pushed, right, the moment D has the value that needs to be pushed, then everything else, then I just push and increment PC. I assume that D has the value to be pushed here, right. Similarly, So then I have to just use this code at whatever code I am marking here at SP to push it. That's all. So, but on the other hand, in the case of POP, suppose in the case of POP, we have POP static index. So again I put at xxx dot index. D equal to A, because we need the address, right, xxx dot address. So D equal to A and then at R13 at R13, and then we can, so actually this is in the case of POP, we can just see what will happen here. Let us go to the POP. We can do much more better than this. So all see, when we looked at POP segment index, I am marking in green here, all this was to calculate the address and all this was to pop to that address. And here I assume that R13 has the address to which we need to pop. So instead of R13 here, which I am using here, I can basically say at, instead of this I can say at xxx dot index. So if your pop this segment is static, then basically I can basically go and say this is at xxx dot index. So rather than right, if it is static, I can just go and say this is xxx dot index. I need not have this part of the code at all, because at xxx dot index will give you the address here. So we just have this part to go ahead. So this is how we do the push and pop. So this is sort of a very large module that we have done so far. I think it's the longest module, but please understand this in this full aspect. We have made an earnest attempt to give you the complete understanding of how the whole arithmetic and the memory access instructions work. And this is extremely important because this is the first introduction to backend of compiler, and I want you to enjoy this and do. Right now we will go into the next module 6.6, where we will do a demo of the project 7. Thank you.